Hi there. Okay, this video is on Z-scores. If you have not done all of the assigned practice up to this point, stop the video, go back and do it. It's not going to make any sense unless you've done the work up to here. Z-scores are completely different from anything you've ever seen before. And they're not difficult. It's just a completely new concept, and you need to come in having the background knowledge about the normal distribution curve. All right, here we go. First thing I want to say is a minor detail. When we've been talking about the normal curve, and we said that 34% of the data is in here and 34 is in here, and what is it, 13.5? I should probably know that. 13.5 and 2.35 out there. Those numbers are rounded. They're good enough for most purposes, and that's okay. The numbers that you see on this drawing here are more precise. They're more accurate. They're also rounded, of course, but they're not rounded as much. And we're just going to use these for right now when we're talking about the Z-score, because what the Z-score does is it lets you map a data point to where it is on the normal distribution curve. That will make more sense in a few minutes, okay? The big picture, the Z-score is a number that gives you how many standard deviations from the mean that a particular data point is, okay? And what that does is it lets us look up in a table to find out what percentage of the data is less than your test point. Okay, so that's really useful. Let's do an example. So the value m on this graph has got a Z-score of 0.36. That means that m, this point, this value m, this is m right here, is 0.36 standard deviations above the mean for whatever this data set represents. So here's our mu is right here in the middle. That's the mean. This is 1 standard deviation, 2 standard deviations, 3 standard deviations. And you can see that it's a little less than halfway, a little more than a third. So this is 0.36 here. If this distance here is 1, this distance here is 0.36. Does that make sense? It matches the graph. Looking this little picture here, this table here is a snippet from a Z-score table, and it's showing you how you read the Z-score table. What you do is the numbers along the first column and along the top of the table are your Z-score numbers, and what you do is you go down first. So this is where you find the 0.3, okay, right there. And so it's going to be somewhere on this row. And then this is the 0.06. So you find the intersection of this. So this cell right here represents the 0.306 of a Z-score. And this number is 6.6406, which equals 64.06%, because it's a percent as a decimal. So you're just going to multiply it by 100 to make it into a percent. So just going to back up a little bit. If the number was 0.32, it would be this one, okay, because that's the 0.3 and the 0.02, so 0.32. If it was 0.18, it would be 0.108. 1 and 0.8 is right there, okay? And I will get you a copy of the Z-score table. I will post one. Now, does this number make sense? 64.06%. If I look at this, does this look like the yellow shaded area here is that 64% of the total area under the curve? And yeah, that's quite reasonable. Okay, so that does make sense. Okay, let's look at another example. What percent of the data set is lower than a point with a Z-score of negative 1.34? So I'm going to pop over to the Z-score table. Okay, here we have our Z-score table, and we are looking up a Z-score of negative 1.34. So we're looking at, so the Z-score table is 2 pages. The front page starts at negative 3.4 and goes to 0. And the second page goes from 0 to positive 3.4, actually 0.349 would be this one down in the corner here. But we're looking for negative 1.34. So I'm going to go down this column and find 1.3. And I will highlight. So it's going to be on this. Sorry, let me redo that. Can't tell which one I'm trying to do there. 1.3. It's going to be somewhere on this row. Oh, I'm not very good at this. It's really hard to do. Okay, there's the 1.3, and it's going to be in the column of 4, so it's going to be on this column somewhere. Okay, so be careful because this is actually the 5th column. You can't don't just count over 1, 2, 3, 4 because the first column is 0, 0. So it's going to be this column. So it's going to be this number right here. Okay, 0.0901. So let's just go back to, okay, so we found that when we looked up the negative 1.34 in the table, we got a value of 0.0901, and that is equal to 9.01%. Okay, and I'm just going to write enabled. This is from the table. Look up negative 1.34. Okay, so make sure that that table is making some sense to you. Okay, example 3. Remember Tony's Huskies? Their weights are normally distributed with a mean of 52.5 pounds and a standard deviation of 2.4 pounds. In the previous lesson, we sketched a graph of the weight distribution, and there it is. And the question is, what percent of adult male dogs at Tony's kennel would you expect to have a weight less than? I'm actually going to change this. I'm not going to use that number. We're going to use the 47.7 pounds instead. Okay, sorry about that. Okay, so we have 2 ways that we can do this. The way that we learned in the last section was we know that this whole section here is 50%, right? Because it's bigger than the mean. This part here is 34.13% using the numbers from the table on the previous page, or the drawing on the previous page. And this section here is 13.59%. So the percent that is greater than 47.7 pounds is 13.59 plus 34.13 plus 50%, which equals, oh, I actually have to redo these calculations because I'm changing the question. 13.59 plus 34.13 plus 50 is 97.72%. Therefore, the percent less than 47.7 pounds is 100 minus 97.72, which equals 2.28%. Okay, so there's our answer doing it the way we knew before. The other way we're going to do it is we are going to, there's a second method. We know that this point right here has got a Z-score equal to negative 2. Um, 47.7 pounds is negative 2, because this has got a Z-score of 0, this has got a Z-score of negative 1, and this has got a Z-score of negative 2. It's how many standard deviations is that from the mean. Okay, so if we look up -2 in our z-score table, let's do this in a different color. It's negative 2.00 right there, and that's 2.28%. This is where I need to go. So you get the same answer. Okay. What percent of adult male dogs at Tony's kennel would you expect to have a weight less than 48 pounds? So 48 pounds would be right about here. We actually can't do that. Okay, we still can't do. Because we don't know the z-score. For 48 pounds. But we will find that, okay? It's actually super, super straightforward. Okay, here is the formula that we can use to calculate the z-score. It's pretty straightforward. Z equals the data value minus the mean divided by the standard deviation, and that's your z-score. You look it up in the table and you find the percent. So let's look at how this works first. What we're doing, essentially the z-score converts any data point in a set for which we know the mean and the standard deviation to its equivalent place in what's called the standard normal distribution curve. So we looked at a normal distribution curve before. The standard normal distribution curve is one that has a mean at 0 here, and then one standard deviation from the mean is at value of 1 on the graph, and then 2 and 3 and 4 and negative, and so on. So the x value of the graph is actually how many standard deviation a point is from the mean, which means it's equal to the z-score. So I've actually got a, will this work? Nope. Okay, I'm gonna, let's go and take a look at this. This is a model of the z-score and showing how it derives from the data points that you have. So here I have, actually there's two graphs, they're just right on top of each other right now. So I'm going to move this one over. And so what I have here is a data set, which is the striped graph over on the right. And it's got a mean of 9.7, and it's got a z-score, or sorry, a standard deviation of 2.85. So there's its mean over here, just to the left of 10, and it's got a fairly big standard deviation, so it's quite a bit flatter. This one on the left here, this is the normal standard normal distribution curve with a standard deviation of 1 and a mean of 0. So we can see that this graph centers at 0, and the line for the one standard deviation is at 1, for two standard deviations is at 2 on our y-axis. And then this lets me change what my test point is. So here I've got a test point of 12.5, and 12.5 I can see is that a z is one standard deviation away from the mean, and if I look at the z-score for that, it's at one standard deviation from the mean. And I actually can animate this. I can press this button here, and it slides the one graph and it morphs it, shoves it over, squishes it, heightens it. There you go. It lands right on top of the other one. I just think that's really pretty. I do know that I'm a nerd. Okay, so let's just pause that right now. I can slide it over myself too. So there, that's it right on top of it, okay? And so I can use any data point. I can move my, my test point to, I can make it 11. So if it's 11, it's not exactly on a standard deviation line, like it's not 1 standard deviation or 2 standard deviations away from something. So I don't know exactly what the z-score is, but if I use my z-score formula and I morph it over here, I can see that my z-score is somewhere. Does it say what my z-score is? Yes, my z-score is 0.456, which makes sense. It's almost halfway between the 0 and the 1. Okay, so this, I will post the link to this demo, and you can play around with this. This actually, I think, would be really helpful when you're looking at questions to help visualize what's going on. Okay, all right, let's go back to the notes. It might help to think of a z-score as kind of being like a percent. A percent lets us compare a score of, say, 26 out of 35, which is 74%, to a score of 41 out of 54, which is 77%. And when I look at the percent, it's easy for me to see which test was a better score. Much easier than it is comparing the 26 out of 35 to the 41 out of 54. Those are like weird numbers to compare. By changing both of those numbers to a score out of 100, it's easy to compare. And the z-score lets us do the same thing. It lets us compare data from data sets with different distribution patterns. As long as they are a normal distribution pattern, we can change them to a common scale, and that helps us do the comparisons. Okay, now we can deal with Tony's dogs with a weight of less than 48 pounds. So, just gonna turn my page here. Okay, so do yourself a favor and write the stuff down, okay? It's easier to find. So our test point, which is x, is 48. This is the test point. And our mean is 52.5. And our standard deviation is 2.4. So we have our formula of z equals x minus mu over sigma. So this is going to be 48 minus 52.5 divided by 2.4, which equals negative 1.875. Now, can you please take your calculator and check that you actually get that? Some of you will get a different number because if you punch into your calculator 48 minus 52.5 divided by 2.4, it's going to do the division first. So remember that you need to do the subtraction first. So whether you put brackets around it or you go 48 minus 52.5 equals and then divided by 2.4, make sure you are getting the negative 1.85. And then I've gotten into the habit of doing this to say that I'm going to the table, and I get 0.03004, which equals 3.04%. I want to just be clear, this number here is the z-score, and what you get from the table is the percent, and that is the answer. The percent in the table is always what is to the left of the data point, the test point, okay? So DIMS, does this make sense? Well, let's just go up to page 19 where we have this fairly accurate graph, and we're looking at 48 pounds, which is right here, and we got an answer of 3.4%. Well, we know that this section here is 2.35, so 3.04%, yeah, that's a very reasonable number for that graph. So I'm just going to put yes, C graph on page 19. All right, example 4. A math test had a mean score of 90 with a standard deviation of 5.6. Mary's score was 62. What percentage of students had a score lower than hers? Well, let's write down what we know. We know that our test point, x, is 62. Our mean is 60 and our standard deviation is 5.6. So now we just need to plug all those into the equation. We get 62 minus 60 divided by 5.6, and that equals 0.357. We don't have a z-score table that goes to 3 decimal places, so we're going to round that to 0.36, and this equals the z-score. And we go to the table, and that gets us 0.6406. So our answer is 64.06% have scores lower than hers. All right. 2 more examples and we're finished this. Okay, example 5. Haley belongs to a running club in Vancouver. Part of her training involves a 200-meter sprint. Below are normally distributed times for the 200-meter sprint in Vancouver and on a recent trip to Lake Louise. At higher altitudes, run times tend to improve. Do you know why? Do you know why? I'm not going to tell you. Compared to the club results, where was Haley's run time better? So her time was faster in Lake Louise, 24.77 seconds instead of 24.95 seconds. But where was it better compared to everywhere else? Everyone else. Let's see. So what we're going to do here is we're going to look at the z-scores. So in Vancouver, her z-score, which is x minus mu over sigma, and that is on your formula sheet, is her runtime is the x, so that's 24.95 minus the mean, which was 25.75, divided by the standard deviation at that place, which is 0.58. So she gets a z-score of negative 1.38. And then this is my little arrow that means to the table. And if I look that up on the table, I get a percentage of 8.38%. And in Vancouver, in that run in Vancouver, she did better than 8.38% of the other people. Nope, wait, I got to get this right. Her run time, I have to draw the picture. I'm sorry, I have to do this because I have to make sure I get this right, and I want you to know how to figure it out. So the mean was 25.75, and her runtime was less than that. Her runtime was 24.95. So this amount here is 8.38% had times faster than Haley because their times were smaller. So there were 8.83% faster than Haley. In Vancouver. Okay, you got to make sure you pay attention to this because we got to, sometimes lower numbers are better and sometimes higher numbers are better. Okay, in Lake Louise, that's Lake Louis, not Lake Louise. Oh no, that's right. Okay, Lake Louise. The z-score is x minus mu over sigma. So in Lake Louise, it's 24.77 minus 25.57 divided by 0.60 gets us a z-score of negative 1.33. We go to the table, that gets us 9.18%. So in Lake Louise, 9.18% were faster than Haley. So she did better in Vancouver because fewer people ran faster than she did. Okay? All right, last example. IQ test. IQ tests are sometimes used to measure a person's intellectual capacity at a particular time. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. So yes, the average IQ score is 100. It is defined as 100. If you have a population who is more educated or whatever and the IQ scores goes up, they change the scale so that the average is always 100 and the standard deviation is 15. Okay, if a person scores 119 on an IQ test, how does this score compare with the scores of the general population? Okay, so 119 is our test point, that's our X. Our mean is 100 and our standard deviation is 15. So Z equals X minus mu over sigma equals 119 minus 100 divided by 15, which equals 1.27. I go to the table with that, 0.8980, so that's 89.8%. So somebody with an IQ of 119 is higher than, their IQ is higher than 89.8% of the population. Okay, before I send you off to do your practice work, I just want to draw your attention to a couple of things here. Because how you write your workout does matter. It makes things easier or it makes things harder. And I'm always a fan of be smart about your lazy and make it easier for yourself. You notice that I write out this formula each and every time. That is how you remember it. Do you remember me saying that to you like 100 times at the beginning of the year? Write it down every time. It doesn't take any time. It helps you remember it. It keeps everything more organized. The other thing I want to say is notice that I do not use an equal sign here because 1.27 does not equal 0.8980, but 1.27 as a z-score leads us to 0.8980 from the z-score table. Okay, so an arrow is okay, an equal sign is not. This is the z-score. Okay, we get z equals, and this is the from the table. This is the percent. This is from the inside of the table. Okay. All right. There you go. That is the lesson for section, the first lesson of section 4. Go and do this practice before you look at the next video, which will be on questions that are actually a little bit more complicated than these ones. All right. Have fun.